Okay, so it is customary to begin this kind of thing by thanking those without whom this wouldn't be possible. And I hope you can hear me all right? Yeah? All right. Okay, so the custom is to thank those without whom this wouldn't be possible. It's a good custom. So let me begin by thanking I'm not sure what the committee is called, but that's the committee that is responsible for Friday night lectures. So let me thank the Friday night lecture committee, the lecture committee, for letting me do this. Let me also thank our deans, our former dean, Mr. McFarland, and our current dean, Ms. Palman, for scheduling this lecture at exactly the time that most sophomores are working through Ptolemy in their math tutorial. So when it comes to a figure like Ptolemy, who is probably not the most entertaining author on the program, for most, I think this is exactly the kind of trick that one has to resort to boost attendance. And I don't know a single sophomore, by the way, so. So I just assume that whoever I don't recognize in the audience is a current sophomore. And finally, and most importantly, I'd like to thank my colleagues, everything that I've learned or understood about Ptolemy in the past 3 years. I don't think I probably didn't even know who Ptolemy was before I came to St. John's. So this is very much a St. John's project. So everything that I've learned about Ptolemy, I've learned with and from my colleagues. And by colleagues, if you think that by colleagues I mean exclusively or even primarily other tutors, you're wrong. It really is primarily the students that I worked through this with the students. So it took me 2 iterations of sophomore math last year and the year before that to really to get what Ptolemy is doing in those Mars chapters. So I'd like to thank those students. It is with them that I worked through this. I should probably also apologize to them for sort of throwing these chapters on them in the tutorial without having much clue about what's going on in those chapters myself. So it was very much like the blind leading the blind, really. But I think, finally, I think by the end of, I think we got most of it by the end of the second section of sophomore math last year. So this is a product, above all, of those 2 years of sophomore math. So I'm especially happy to see some of those students here. Okay, so I think the preface part is over now. So let me just jump into my lecture, and you have handouts, and I hope that there were enough handouts for everyone. I don't think there's really anything that you need to know sort of in advance about the handout or how it's structured. Number 0 on the handout is just the abstract as well as the first few sentences of my introduction. So for the first few seconds of my lecture, you can follow along. And then after that, it's mostly quotes, a few diagrams. I try to keep the diagrams to the minimum. One reason for that is that I found it really difficult to draw these. By the way, I should mention that these diagrams I drew on, and at least the seniors here will understand what I'm referring to. I drew them on Sideboard. I couldn't, or they weren't turning out very well on any of the, on Google Docs or anything like that. So at the end I just went back to Sideboard at the end of the day, and I think it worked. They look fine. And by the way, I should also say that if you find it strange that we are in the Great Hall as opposed to the FSK, I just wanted to see your faces sort of better, to be closer to the audience. That's why I asked Ms. Palman to do it here. Although now, with the Sideboard thing and this lecture happening in the Great Hall, this really feels a little bit like kind of a throwback to the COVID year, the academic year 2021, because that's where, well, except for the masks. Maybe I should have distributed the masks at the entrance. Okay, all right. So Ptolemy's bisection of Mars's eccentricity. The Almagest provides very little insight into how Ptolemy arrives at his hypothesis and models. Ptolemy's secrecy is especially regrettable when it comes to the so-called equant. The powerful, yet potentially heretical, and I will say a few words about that later in the lecture. The powerful, yet potentially heretical mathematical tool that is arguably Ptolemy's most important personal contribution to astronomy. Ptolemy's equant makes it possible to divorce the center around which the planet describes a circular orbit, a circle, from the center around which its motion is uniform and even. In this lecture, I shall argue that even though Ptolemy first introduces the equant in his account of the inferior planets in Book 9, specifically in Chapter 3 of Book 9, on Venus, he first developed the equant hypothesis in his encounter with the superior planets, Mars in particular, that only make their appearance later. Book 10, chapter 7, that's the chief Mars chapter. So in this lecture, I shall attempt to defend the Martian origins of the concept of the equant against the rival hypothesis of the equant's Venusian origins. I find the Martian hypothesis more attractive than the rival. That's the first natural reason why I shall try to defend that position. What's more, and this is both unfortunate and understandable, the reason why I want to look at Mars is that the Mars chapter are frequently skipped over in sophomore math tutorial at St. John's. So not only does the majority of students take the Venus chapter of the Almagest as the account of the equant, as Ptolemy's account of how he arrived at the equant, they do not even get to experience the enduring testing journey that Book 10, Chapter 7, the Mars chapter is, which is kind of a pleasure in itself, although of a painful kind. So if my lecture is endurance testing, then it's Ptolemy's fault, not mine. Okay, my lecture will move through three main stages. In part one, I shall briefly discuss Ptolemy's distinction between the inferior and the superior planets, or inner versus outer planets, as well as, again, quite briefly, his approach to Venus and his discovery of Venus as equant. In part two, I shall say a few words about not just the equant's first appearance in the Venus chapter, but also why I suspect that Ptolemy did not arrive at the equant in his encounter with Venus, even though that's the reader's first introduction to the concept. In part three, I shall work through Ptolemy's investigation of Mars fairly closely, focusing on that endurance testing, Book 10, Chapter 7. Most importantly, I shall try to reconstruct how and at what point Ptolemy realized that the theory of Mars requires this notorious equant. That is, that the center around which Mars describes a circular path could not be the same as the center around which it revolves uniformly. Okay, part one, or section one, two kinds of planets. The order of the Almagest must be familiar to you, or at least the planet books. First, Ptolemy tackles the sun, then the moon, so that's book 3. I take it that everyone, at least all the sophomores, have already looked at that chapter. Then Mercury, followed by Venus, and finally Mars, Jupiter, and Saturn. So it seems like the rule is that the Almagest treats the inner planets before the outer planets. I think that's true even in the retrogradation chapters later in the book. So that seems just to be like a kind of a general rule for Ptolemy. But it is far from clear that this is the order, right? The order in which the Almagest presents itself. It is not clear that that is the order in which Ptolemy developed his theories. Ptolemy could have developed his planetary models in a quite different order or without a discernible order. Ptolemy does not hide that the structure of the Almagest is determined by tradition, convention, we might say, and that's quote number 1 on the handout. All the foremost astronomers agree that all the spheres are closer to the Earth than that of the fixed stars, and farther from the Earth than that of the Moon, and that the spheres of the three superior planets, outer planets, are farther from the Earth than those of the other two and the Sun. Saturn's being the greatest, Jupiter's the next in order towards the Earth, and Mars below that. But concerning the spheres of Venus and Mercury, we see that they're placed below the Sun sphere by the more ancient astronomers. So to say that the order of the Almagest is purely conventional may be slightly unfair to Ptolemy, but Ptolemy certainly doesn't provide any good reasons, any rational reasons, or any reasons of his own for why the order of the treaties is as it is, or why he considers Mercury and Venus inner planets, while Mars, Jupiter, and Saturn are categorized by him as the outer planets. And it is indeed somewhat strange that, at least in the Almagest, he doesn't himself really engage with the order of the heavenly bodies. He doesn't take a kind of a position of his own as far as that question is concerned. So Ptolemy divides the planets into the outer and the inner. As far as the superior planets are concerned, or the outer planets, there is no limit to the angular distance or elongation that they reach from the Sun. But there is a limit to the inner planets, Venus and Mercury, elongations from the Sun. Mercury and Venus never stray too far from the Sun, but appear to revolve around it. Right? Mars, Jupiter, and Saturn behave in a completely different way. They can be spotted anywhere along the ecliptic, even opposite the Sun. This is why Venus and Mercury have been known to appear in the sky as the morning star or the evening star in the early dawn hours or just after the sunset. So quote number 2 on your handout, this is Ptolemy's summary of the inferior versus superior planet distinction. And the syntax here is a little bit, at least at first blush, it's a little awkward because of the use of the comparative, so just bear with me. For, by putting the Sun in the middle, it's also taken out of context. Well, not out of the context, out of the paragraph. For by putting the Sun in the middle, it is more in accordance with the nature of the bodies, in thus separating those which reach all possible distances from the Sun, and those which do not do so, but always move in its vicinity. So ultimately, the superior versus inferior distinction in Ptolemy stands for nothing other than the distinction between unlimited versus limited elongations. That's what matters for Ptolemy. Perhaps that's the only thing that matters for Ptolemy about this distinction. So although Ptolemy's approach to the inferior planets, as we're about to see, differs from his approach to the superior planets very much, if Ptolemy categorized Mercury and Venus as superior planets and Mars, Saturn, and Jupiter as inferior planets, nothing about the treatise would have been different effectively. Right? In other words, if Ptolemy decided to call those planets that exhibit unlimited elongations inner planets, and those that exhibit limited elongations superior planets, wouldn't change anything. So the distinction in the inner and outer planets really just is the distinction between these two kinds of elongations that the planet can have. At least practically, that's all that distinction means and does for Ptolemy. Ptolemy finds the inferior planets as rather convenient for his model building. On the other hand, as we will see, that Mars, Jupiter, and Saturn can be spotted anywhere along the ecliptic with regard to the Sun is for Ptolemy a serious complication. Now, most convenient about the inferior planets, and this is something that Ptolemy makes clear in quote number 3 on your handout, is that it is obvious from the greatest elongations for Mercury and Venus when the planet is at the point where the line of our sight is tangent to the epicycle. So what's convenient about Mercury and Venus is that their motions around the Sun make the epicycle visible, as it were. There's indeed something intuitive about picturing these planets as orbiting the Sun on an epicycle, whose radius will match the angular distance that the planet from the Sun, the planet's angular distance from the Sun. Thus, Venus's elongations provide Ptolemy with a quick and sure way to geometrically determine the size of the planet's epicycle. However, And this is the chief complication as far as the inner planets are concerned. However, since the planet's elongations are variable, Ptolemy must place the epicycle on an eccentric deferent. In this way, Ptolemy makes the variation in angular distance from the Sun into a function of the epicycle's distance from the observer, who is no longer at the center of the circle carrying the epicycle. So there isn't really a proper diagram for Venus on my handout, but the diagram under number 10, which I'm later going to use to say a few words about the retrograde arcs of the planets, could be used, or essentially depicts in its most simple kind of crude way what the Venus model looks like. So the observer will be at C, but the real center around which the epicycle is orbiting is at D. And so that distance allows Ptolemy to, at the same time, be able to say that the radius of the epicycle is fixed, but also take care of the apparent variation in the distance that Venus has from the Sun. So the apparent radius is variable in function of the distance of D from C and where the epicycle is on the circle, the carrier circle, which is standardly referred to as the deferent. Okay. So let me now provide a very brief account of Ptolemy's Venus chapter. It's brief, or it will be brief, because I assume and I hope that most of you have kind of at least a very rough idea of how the model of Venus works. And I will then use Ptolemy's approach to Venus and his model of Venus as a kind of as a background, as something to compare the Mars model that I'm gonna work through much more closely with. Okay. So Ptolemy's first step in the Venus chapter is to identify the planet's line of apsides. So on diagram 10, that's a straight line through the diameter of the bigger circle through points D and C. It's called the line of apsides because it connects the planet's apogee and perigee, so the point where the epicycle is closest to the observer at C, and the point where it's farthest from the observer. So perigee is the closest, apogee is the farthest. On this line of apsides, as I've just indicated, the ecliptic center and the deferent center will both be situated once Ptolemy determines where they are, their position. Now, Ptolemy best describes the procedure that he employs for finding Venus's line of apsides, not in the Venus chapter, but in the Mercury chapter, because that's the inferior planet that is tackled first in the Almagest. This is, by the way, one of the difficulties of reading the Almagest not in its entirety. Often one feels like an explanation is missing in a given chapter, and frequently, perhaps not always, but frequently the reason for that may be that Ptolemy has already provided that explanation in an earlier chapter where he's employing an identical procedure. So he's just assuming that the reader is already familiar with the procedure. But of course, if you're sort of picking and choosing chapters, then you're in trouble, as it were. Okay, so quote number 4. From the Mercury chapter, that is describing the procedure used for both planets for finding the line of apsides. We sought out observations of greatest elongations in which the distance of Mercury as morning star from the mean longitude of the Sun, from the mean longitude of the planet, is equal to its distance as evening star. For once we had found such a situation, it necessarily follows from our demonstrations that the point on the ecliptic halfway between the two positions of Mercury as morning star and evening star occupies the apogee of the eccentric, right, the line of apsides. So what Ptolemy is doing here is he simply assumes orbital symmetry. He assumes that the orbit is symmetrical. And so to discover the line of Apsides for him just means discovering the axis of symmetry, right? The line dividing the orbit in two mirror-like halves. What is required for that is finding Venus's greatest western elongation that is equal to its greatest eastern elongation. And once you find such a pair, he simply draws a diameter, draws the line sort of halfway between them, and that's going to be the line of Apsides. So that's what he does in Almagest 10.1. He discovers the axis of symmetry for Venus, and in the next chapter, in 10.2, he establishes which end of that apsidal line is apogee and which one is perigee. Which, again, the procedure is fairly straightforward and simple. The end that is producing greater separations has to be the perigee, because that's the point where the epicycle is closest to the observer, and vice versa. So the other end then is the apogee. So, although the epicycle of Venus has a fixed radius, the apparent radius grows when the planet approaches the perigee and shrinks when the planet approaches the apogee. This variation is what enables Ptolemy to also establish the planet's eccentricity. What eccentricity means is simply the distance between the center C, where the observer is, where we are, and center D, which is the real center around which the epicycle is revolving. Since the variation in apparent distance is a function of that distance, of how far D is from C, he uses the variation to establish exactly what the distance is, right? And that means that he has found the eccentricity. But, as we are about to see, two centers, so C and D, will not be enough for Venus. So the single eccentricity model will not be enough. So let me now transition to part 2 of the lecture. The genesis of the equant. It may seem, as I've just said, that Ptolemy's model for Venus is finished in Book 10, Chapter 2. But in truth, it is not. Ptolemy is not done yet, and Chapter 2 is followed by another Venus chapter, Chapter 3. This is how Ptolemy begins Chapter 3. And this should be quote number 5 on your handout. But since it is not clear whether the uniform motion of the epicycle takes place about the deferent center, here we took two greatest elongations in opposite directions, in each of which the mean motion of the sun was a quadrant from the apogee, so 90 degrees from the apogee. That's what he calls quadrature. This is the first appearance of the equant in the Almagest. The center of uniform or even motion that is separate, divorced as it were, from the center of the deferent, not to mention the ecliptic center. Now, in fact, Ptolemy announces the equant even earlier than that, as early as Book 9, Chapter 5, in his general introduction to the planetary hypothesis. So here's another quote, 6. Now, from prolonged application and comparison of observations of individual planetary positions, with the results computed from the combination of both the above hypothesis, eccentric, epicyclic, we find that it will not work simply to assume, as one has hitherto, that the excenter on which the epicycle center is carried is identical with the excenter with respect to the center of which the epicycle makes its uniform revolution towards the rear, cutting off equal angles in equal times at that center. So although that's, technically speaking, although this is also not quite true, as I hopefully will show in just a little bit, so although technically speaking the equant is introduced as early as 9.5, in flesh it is first introduced in the Venus chapter, so 10.3. Ptolemy employs a number of different terms to describe the equant. The equant is not his term. That's the term that sort of later astronomers of the working in Latin language devised for this mathematical tool. Ptolemy calls it, and this is always a mouthful really, the point about which the uniform motion of the epicycle takes place. That's probably the term, the phrase that is used most frequently to describe the equant. But he also calls it the center of the eccentric producing the anomaly, or even, much simpler, the greater eccentricity, as well as the second eccentricity. And why he calls it the greater eccentricity will hopefully become clear in the course of the lecture. Okay, by introducing the equant, Ptolemy assumes that the planet's angular speed is uniform with regard to a center that is distinct from the center around which the epicycle traces a perfect circle. So if the deferent center now becomes the center of equal distances, the center of equal distance and of distance alone, so the center that is assuring that all the radii are equal, which is what makes a circle. The epicycle is now exclusively the center of even or uniform motion. This is quite strange. I mean, when one reads it for the first time, one should find it very strange. Once the equant is introduced, the epicycle circular motion in deferent is no longer uniform. And its motion on the equant, or its motion around the equant center, is no longer circular. Unless you could sort of draw an equant circle, right, and kind of project where the planet is on it. But I'll say a few words about that later. Okay. Although I shall not tackle this issue here, it is not surprising that many view Ptolemy's double eccentricity hypothesis, so this model that has both the equant and the deferent center, this strange model, as a grave violation of the principle of uniform circular motion that he introduces as early as Book 1 of the Almagest. Right? This is where he tells the reader that it is the mathematician's task to reduce all heavenly phenomena, to show that all heavenly phenomena are or take place by uniform circular motions. So this is indeed strange that or it's a strange moment when he introduces the double eccentricity model. Some have argued, Neugebauer, for example, who's a great scholar of Ptolemy, that the equant hypothesis, what the equant hypothesis effectively produces is the factual abolition of the dogma of uniform circular motion in a strict sense. So it might be the case, when all is said and done, that Ptolemy is responsible not for establishing the dogma of uniform circular motion, as I think is often assumed, but for demolishing it. So he doesn't sort of start that dogma. He doesn't even maintain it. He demolishes it. Although I recall 2 years ago, my colleague, Mr. Borsima, who I thought, right, I saw on the second floor, argued that there's nothing strange about the equant because in the phrase uniform circular motion, there's a comma between uniform and circular. And I find that fairly convincing, actually. I mean, whoever said that they have to coincide in one center? That's what the comma is for, to sort of prepare us for the equant. Okay, so just a few more things I want to say about 10.3 and the introduction of the equant, and then I'll move on to my suspicion and Mars. So in Almagest 10.3, the equant is introduced in response to the failure of the single eccentricity model, so the model that only has D and C centers, the model that was developed in Chapter 2, to predict Venus's angular distance from the Sun at quadrature, so 90 degrees from the apogee. Ptolemy discovers that the difference between Venus's elongations, eastern versus western, at quadrature is greater than the model of Chapter 2 predicted. But if the difference between Venus's separation is greater than anticipated, then that means that at quadrature, the epicycle is farther from the ecliptic center than anticipated. In other words, Venus is just too slow in the first quadrant of the orbit, and then too quick on the opposite side of the deferent circle. So it's too slow, and it falls behind where it should be, according to the model of chapter 2. Now, Ptolemy's solution to Venus's slowness, and this is the equant, is to move the center from which we evaluate whether the motion is uniform farther from the ecliptic center, so even farther from the ecliptic center than the deferent center, divorcing one from the other for the first time in the treatise. And in this way, Ptolemy boosts, as it were, the angular distance that Venus has traversed by the time it reaches quadrature on the deferent. So from the equant center, Venus no longer appears as slow and tardy because Ptolemy has just granted it a greater arc, right? Sort of by moving that center up. It is vital to note here that the equant center does not supersede the deferent center. In its actual position, Venus must be located on the deferent circle. And I put actual in quotation marks to indicate that, on my reading at least, Ptolemy's model is not physical and realist. Venus isn't actually there on the deferent or the epicycle. And ultimately, this is just a model for computing and predicting the behavior of Venus. And I have this sort of footnote, side note, to hopefully provoke questions about that in the question period. Okay, if Venus's new equant assumed the function of the deferent center, this is why we have to have both, right? The equant does not supersede the deferent center. If Venus's new equant assumed the function of the deferent center, then at syzygy, so apogee or perigee, that's the term that Ptolemy uses to refer to both at once, the variation in Venus's separation from the sun would be too great. So we would end up with the same problem as chapter 3 first introduces, but sort of from the opposite end. Right? So that wouldn't agree with Ptolemy's observations, and this is why Venus must have not one, but two excenters, and this is the double eccentricity model. So at this juncture, the diagram 10 on the handout no longer corresponds to Venus's model because it only has two centers, so this is the single eccentricity model. Where exactly that third center is going to be placed, well, hopefully that will become clear fairly soon. So there are many commentators and scholars who trace Ptolemy's discovery of the equant to his investigation of Venus. So at least at this point in the treatise, they take the order of presentation to correspond to the order of Ptolemy's discovery. But it is hard to resist a suspicion that the Almagest 10.3 is a setup. Ptolemy considers Venus's quadrature or Venus at quadrature because he already knows that that's where the single eccentricity model will prove inadequate. And since it is not certain that the order of the Almagest is the same as Ptolemy's order of discovery, there are many moments where that just can't be true in Ptolemy, it is not unreasonable to ask whether the genesis of the equant might be linked to a planet other than Venus. So that's what I shall try to ask and try to explore an alternative Martian hypothesis of the equant's genesis. Perhaps, although the chapters on the superior planets come later than the chapters on the inferior or inner planets, it is perhaps Ptolemy's struggle with the superior planets, and Mars specifically, that alerted him to the notion or to the necessity of introducing the equant. Okay, the end of part 2. Part 3, the equant of Mars. Ptolemy's treatment of the outer planets, and I'm going to focus on Mars, differs drastically from his approach to the inner planets, for reasons that I've, in fact, already hinted at. Since Mars exhibits unlimited elongations, so it can be found anywhere in the ecliptic with regard to the sun, it doesn't follow the sun in the same way as Venus and Mercury do. It is not possible to deduce the size of Mars's epicycle from those elongations. So the first step that Ptolemy takes in his investigation of Venus is just not possible for Mars. So he has to come up with a new procedure, a different procedure. So what Ptolemy comes up with is he decides to focus on the planet's oppositions to the sun. When Mars is on the opposite side of where we are, the Earth, from the sun. As Ptolemy explains in 10.6, and this is quote number 7 on the handout, the demonstrations of superior planets cannot proceed along the same lines for these planets as for the previous two, since these reach every possible elongation from the sun, and it is not obvious from observation as it was from the greatest elongations from Mars, from Mercury and Venus, when the planet is at the point where the line of our sight is tangent to the epicycle. So his approach is going to be, in a way, the opposite, the photographic negative of his approach to Venus. If, in Venus's case, the elongations make the epicycle visible for Ptolemy, and that's what Ptolemy is looking for, in the case of Mars and the superior planets in general, Ptolemy picks the observations that do the opposite, that make the epicycle invisible. So those observations where Mars coincides or aligns with the center of the epicycle. As if, right, so those observations where it looks as if the motion on the epicycle of Mars does not exist. That's how Ptolemy phrases it. So Almagest 10.7. Ptolemy's first goal is to determine Mars's eccentricity and the direction of the apsidal line, the line of apsides. To this end, Ptolemy picks 3 observations of Mars about 4 years apart. So 3 observations of Mars at oppositions to the sun, and each is about 4 years apart. So I mean, you can immediately notice, right, that these are not very frequent phenomena. And once he has picked those 3 observations, he immediately has access to, or he can immediately employ, on the one hand, the angles or the arcs of apparent motion between those oppositions, though they're accessible through observation. We measure sort of the arc. Second, he has access to the angles of uniform motion between the oppositions from the equant center. He has access to these arcs or intervals because he has already constructed the table of mean motion in Almagest Book 9, Chapter 4. So those tables tell us how Mars would move or how Mars would behave if its motion were completely uniform. So what those tables then give us is precisely the intervals between Mars's oppositions from the equant center, that is, from the center of uniform motion. So far, or at least at this juncture, it looks like Ptolemy's task is very, very straightforward. Since Mars appears under one set of angles from where we are, C, and another set of angles from E, the task is to establish the position of E with regard to C. That's how one determines eccentricity. So I do have a diagram for Mars. This is 8 on the handout, but it may be a bit too early to look at it because that's the final model, which has 3 centers. Right now, I am speaking of Mars as if we didn't know that it has to have 3 centers. It only has 2 centers. Okay, so this procedure that I've just described a second ago is very familiar for Ptolemy, for this is exactly how he determined the sun's eccentricity in the Almagest Book 3, Chapter 4. Indeed, and this is why I said that it's not technically true that the equant is first introduced in Book 9, in that quote number, I thought that was, quote number 6, I think, on the handout. So that's, in a certain way, that's not the first appearance of the equant on the scene. The first appearance of the equant is Book 3, Chapter 4. And the reason for that is that the sun's eccentric model, the way that Ptolemy develops the sun's eccentric model is by matching the arcs of apparent motion of the sun with the arcs of mean motion of the sun. So he is looking at the apparent arcs versus the arcs of uniform motion, the mean arcs. Those latter arcs are arcs on the equant circle, even though Ptolemy doesn't explicitly say that. Since the sun's model is a single eccentricity model, Ptolemy simply doesn't thematize the sun's equant in Book 3. Ptolemy only thematizes the equant as the center of even motion when it no longer coincides with the center of equal distance. In the case of the sun, it does coincide with the center of, well, the sun doesn't have a deferent. But because that separation of two centers, that breaking apart of two centers, to put it even more dramatically, doesn't happen, Ptolemy never calls the sun's center of uniform motion the equant. But that means that there is a way in which it is the deferent center, as distinct from the center of uniform motion, that is Ptolemy's real innovation in Book 4 of the Almagest. So from a certain perspective, the novelty is the deferent center, not the equant center. Okay, now if Mars's center of uniform motion were the same as the deferent center, and I'm going to call the letter that I picked for the deferent center is, the letter for the deferent center is already familiar to you, that's D. The letter for the equant center is going to be E. So if E coincided with D, Ptolemy's determination of Mars' eccentricity would have reached its conclusion. The model would have been finished. But it doesn't. It turns out that section of Book 10, Chapter 7, which ends or which finishes with Ptolemy's first determination of eccentricity from matching the arcs of apparent motion with the arcs of uniform motion, is only preliminary. By the way, I'm not sure how useful and necessary this is, but I do have a table at the very end of the handout, which is, well, I'll return to it, but for now, I think it might be sufficient for you to just know that under first iteration, I have the data for these two sets of arcs that he compares to come up with the eccentricity of 13, let me just call it 13.7. So that's the eccentricity that results from the first iteration. That's the distance between C and D in the case of Mars. But the model is not finished yet. Let me ask then, why is Ptolemy's procedure not over at this point? Of course, the short answer is because E does not coincide with D for Mars, indeed for all the planets. So Mars will require a more complicated double eccentricity model. But how could Ptolemy establish the insufficiency of the single eccentricity model for Mars? What about Mars could have alerted Ptolemy to the possibility that E does not equal D? And what I'd like to suggest, my contention, is that in the case of Mars, a story can be told about what alerted Ptolemy to that possibility, that E does not equal D. Whereas in the case of Venus, it's much harder to tell that story, perhaps impossible. So I repeat, my question is, what about Mars could have alerted Ptolemy to the necessity of the equant? In principle, the preliminary Mars model could be tested against another set of observations in a way that would be similar to what Ptolemy does in Venus's case. But Mars's oppositions are rare, and the Almagest reports no oppositions other than those utilized in 10.7. What we've just looked at, what's in that table. Yet there might be another independent verification procedure that could have alerted Ptolemy to the possibility of a differentiation between the equant center and the deferent center. Mars's retrograde arcs. So those arcs that Mars traverses, at least apparently, sort of backwards. It's the same phenomenon that Venus and Mercury display. And there's a quote, there's a line, there's a sentence in chapter 6 of book 10 in the Almagest where I think Ptolemy suggests as much, or he hints at precisely this kind of verification through retrogradation arcs. This is quote number 9. This is his general introduction to the superior or outer planets. So he is he's speaking of the outer planets exclusively. Right? Venus and Mercury, at that point, we're already done with. So quote number 9 on the handout. In the case of each of these planets, too, using rough estimation, the eccentricity one finds from the greatest equation of ecliptic anomaly turns out to be twice that derived from the size of the retrograde arcs at greatest and least distances of the epicycle. I take this as an important hint. It looks like, minimally, from this quote, I think one sees that retrograde arcs were used in one way or another in the investigation or in the determination of the superior planet's deference center and center of uniform motion. Of course, you could object at this juncture that Ptolemy could have employed retrograde arcs as a verification procedure for Venus too. But I take it as no accident that this retrogradation hint is found in his account of the outer planets, not the inner planets. So I take that sort of as maximally seriously to make my case. And if we take it seriously, then Ptolemy must have realized that the center E could not be Mars's deference center precisely by investigating Mars's retrograde arcs. So that's book 12 of the Almagest. In the first chapter of book 12, Ptolemy shows that for a retrogradation to occur, the planet must travel on the epicycle an arc greater than the arc that the epicycle itself travels through an angle at our eye, so from the visual center at C. By contrast, when the speed of the planet on the epicycle is equal to the epicycle speed from C, the planet reaches a station, or an appearance of a station, briefly stopping, appearing to stop. This is, by the way, the diagram 10 on the handout, where I've also included the ratio that determines, that yields the station moment for the planet. It's not really important for what I'm doing here, but I thought I would include it. What is important is, let me resume here, that since the size of retrograde arcs varies along the ecliptic, Ptolemy assumes that this variation occurs due to the variation in distance between the observer at C and the epicycle that is carried on a center not at C but at D. Right? So he's using really the same trick, the eccentricity trick, to take care of the variation of retrograde arcs along the ecliptic. But this is why, because he's using the same trick, the eccentricity of the deferent impacts the size of retrograde arcs, while the eccentricity of the equant does not. That is, the greater is the eccentricity of D, the more extreme will be the difference between the size of the epicycle at the apogee versus the perigee. And so retrograde arcs will then be either too long or too short vis-a-vis the observations. If we get the size of the if we get the size of the apparent radius wrong, because the position of the deferent is wrong, then where our calculations of the retrograde arcs will simply not match the observations. So this could be the moment, all right? This could be the procedure that Ptolemy intentionally or perhaps unintentionally used, the procedure that alerted him that the position for D in the case of Mars, that the position that E has could not be the position for D, the position around which the epicycle is actually carried on its carrier circle, the deferent. And it has to be Mars out of all the outer planets for the very simple reason that the eccentricity of Mars, the first eccentricity, 13.7, is really incomparably greater than the eccentricity of the Jupiter or the eccentricity of the Saturn. So in Mars's case, the discrepancy would be not only most noticeable, it would probably be only noticeable in the case of Mars. The eccentricity of Mars is really, I think, I'm not providing the ratio yet, but let me sort of jump ahead and tell you that the ratio of the radius of Mars's epicycle to the radius of its eccentric is almost 2 to 3. So the epicycle of Mars is really very large. Therefore, any mistake that you make in determining its parameters will be very noticeable in a kind of in some independent verification procedure. And I think this is what happens with the retrograde arcs. And this is why Ptolemy has to discard the equant center as the carrier of the planet's epicycle, replacing it with another center. That's finally center D, the center of the deferent. Indeed, Ptolemy's single eccentricity model is only a preliminary model. It must be revised by finding a new location of the center around which the epicycle is carried in a circle. And this is what substantially complicates the trial and application procedure of Chapter 7 of Book 10. That's why it's so long. Ptolemy best describes the nature of this complication, as well as his strategy for dealing with it, in the crucial passage at Heiberg, page 3 to 4. So this is in Chapter 7 of Book 10, and that is the longest quote on your handout, quote number 11. I'm going to read it, and as I read it, I would encourage you to match the arcs and the lines with the diagram on 8. Right? So 8 and 11 go together on the handout. Now, if arcs FZ and ZH of the eccentric equant were subtended by arcs KL and LM of the ecliptic, that would be all we would need in order to demonstrate eccentricity. I'm going to explain what this quote says after I'm finished, but for now, let me just read through it. However, as it is, they subtend arcs AB and BG of the middle eccentric, which are not given. The middle eccentric is, he's referring to the deferent center, because it's, as it will soon become apparent, it's located in between the equant center and the ecliptic center. So subtend arcs AB and BG of the middle eccentric, which are not given. And if we join CSF, CTZ, CHY, we again find that arcs FZ and ZH of the eccentric equant are subtended by arcs ST and TY of the ecliptic, which are obviously not given either. Hence, the difference arcs KS, LT, and MY must first be given in order to carry out a rigorous demonstration of the ratio of the eccentricity, starting from the corresponding arcs FZ, ZH, and ST, TY. But the latter cannot be precisely determined until we have found the ratio of the eccentricity and the position of the apogee. However, even without the previous precise determination of eccentricity and apogee, the arcs are given approximately, since the difference arcs are not large. Therefore, we shall first carry out the calculation as if these arcs, ST-TY, did not differ significantly from the arcs KL-LM. Okay, so now let me try to explain what's going on here. The critical issue is, if Ptolemy, or once Ptolemy assumes not single but double eccentricity, the apparent intervals or arcs, so observations from C, do not subtend or align with the intervals of Mars's uniform motion on the equant circle. So KL from C arc KL, simply does not subtend, does not align with the arc ZF, which is the arc, the same arc as it were, of Mars's uniform motion on the equant circle, which is centered on E, the equant center. Here's why. While the planet's actual position on the deferent and its projected, as it were, position on the equant circle must lie in a straight line with the equant center E, so that's the line through EAF, for example. For otherwise, the planet would not be moving uniformly. So in other words, to be able to say that Mars is moving uniformly from the equant center, the ray from the equant center has to pass through the actual position of Mars in the deferent, right? This is all that this means. Okay, so that was on the one hand. On the other hand, while the planet's apparent position on the zodiac circle, so this is where we spot it, and the planet's, again, actual position on the deferent must lie in a straight line with the ecliptic center C, for otherwise you wouldn't sight the planet. In other words, the ray of your sight has to ultimately hit the planet on a deferent circle. Otherwise, you wouldn't be sighting the planet that you think you're sighting. So while these two sort of alignments are necessary, right? Equant position, deferent position, zodiacal or ecliptic position. The planet's position on the zodiac circle, so that zodiacal position, and the position of the planet on the equant circle, those two do not have to align. They do not have to lie on a straight line from C. In other words, since Mars is actually on the deferent circle, everything must pass through the position of Mars in the deferent circle. The rays of vision yielding the apparent arcs of Mars on the one hand, and those equalizing rays from the center of uniform motion on the other hand. But while from E, the deferent arcs subtend the equant arcs, and from C, the apparent arcs subtend the deferent arcs, the apparent arcs do not subtend the equant arcs. So I'm just repeating sort of the same idea for the third time because I think it's really crucial, but it is also potentially confusing. So Ptolemy finds himself in a kind of a double bind here. To calculate where D is, that's what we're after, he first has to calculate where E is, the equant center. But to calculate where E is, rigorously and with precision, the apparent arcs must be aligned with the equant arcs, which they're not. So to calculate where E is, Ptolemy must calculate the difference arcs. That's KS, LT, and MY. Because those will tell us by how much the apparent arcs sort of fail to align with the equant arcs. But then again, to calculate those difference arcs, he must know where D is. So there's a kind of a circle that seemingly there is no way to exit. Ptolemy's solution, Ptolemy's way to exit that circle or that double bind is simply to assume temporarily that Mars's apparent intervals and the intervals of uniform motions do align. Ptolemy decides to proceed as if the model of Mars were a model of single eccentricity, where E equals D, transferring the epicycle's path onto the equant circle. Or alternatively, Ptolemy has to proceed as if C, K, and F, C, L, Z, and C, H, M were straight lines, but they're not. And for this particular articulation, though this particular articulation of the problem I borrow from another colleague of mine, Ms. Kemmeyer, who is not here, so there's no reason for me to really attribute this to her. No, Ms. Kemmeyer apologized for not being able to make it. Okay, so that is, this kind of a roundabout way, is the preliminary determination of Mars's eccentricity and the line of apsides that, in fact, we've already looked at. The result of that procedure is this first result on the table. But I have reversed my order of explanation so far as if Ptolemy were not aware that E does not equal D, and that his calculations therefore were only approximative, right? So I try to imagine what this would look like if Ptolemy really just thought that E and D must coincide in the case of Mars and calculated it in that way with that assumption. And although Ptolemy, of course, was aware that E does not equal D on those pages of the Almagest, if he weren't operating innocently, as it were, and according to the single eccentricity model, the procedure would possibly, likely look the same. But then he would realize his error, and so he would transform the procedure slightly. Okay, so I think we're close to the finish line here. Having calculated the preliminary value for Mars's eccentricity, Ptolemy restores the difference between E and D double eccentricity. It's a really easy to miss moment in chapter 7 where Ptolemy simply says, draw the additional line AD. That's how he restores double eccentricity. He introduces center D. Ptolemy assumes here that the deferent center D is positioned halfway between C and D. And this is quote number 12 on the handout. The eccentre on which the epicycle center is carried is described on a center which is the point bisecting the line joining the center of the ecliptic and the point about which the epicycle has its uniform motion. When Ptolemy realizes that the value for Mars's eccentricity is too large, so that's 13 something, he decides to try half that value. That's how I'm reading what's happening here. So he simply bisects it. This seems like a natural step in Ptolemy's trial and error approach to Mars. Any other step would probably be more arbitrary and more effortful, right? If you know that a value is too large, the first step to test what the real actual value that you're looking for might be should probably be, or would be in most cases, just to try to bisect or half the original value and see what happens. As Ptolemy's luck has it, however, EC bisected happens to be the correct position for the deferent center. Indeed, not just for Mars, but for all the planets. From the restoration of double eccentricity result Ptolemy's difference arcs, so KS, TL, and YM. By means of these arcs, Ptolemy evaluates the error, albeit intentional error, committed by his initial identification of the equant center with the deferent center. Now, the difference that Ptolemy's difference arcs indicate is the difference between two arcs, both of which lie on the ecliptic center. And this is, by the way, what took me almost 2 years to understand. So at least for me, this was a very confusing point in the procedure. Okay, so difference arc indicate the difference between two arcs, both of which lie on the ecliptic center, so the ecliptic circle, so the circle centered on C. On the one hand, the first arc is the arc of apparent motion. That's what we took from observations. So the fourth and fifth column on the handout, on the table on the handout. And the second arc is the arc, I'm quoting Ptolemy here, taken with respect to the eccentre. That's all he says about that second arc. And it is not clear, or it's not immediately clear, which eccentre, the equant eccentre or the deferent eccentre, Ptolemy has in mind here. But, and we've already seen an instance of this, he expresses himself much more clearly in the Jupiter chapter, where Ptolemy employs the same procedure as in his treatment of Mars, although the Jupiter chapter comes after the Mars chapter. But still, there some things are just articulated more clearly. So this is quote 13 on the handout. Hence, we calculate the apparent intervals of the planet taken not with respect to the excenter carrying the epicycle center, but with respect to the excenter producing the mid-motion. So he must have the equant center, the equant excenter in mind there. So if the arc of apparent motion is formed by the rays passing through the apparent position of Mars, where we spotted it from C, and then Mars's actual position on the deferent circle. So this is CKA on the diagram 8 on your handout, CLB, or, I suppose here it's reversed, CGM. So that's the arc of apparent motion. He's going to compare that and find the difference with the arc taken with respect to the excenter, so this is that much more ambiguous arc that is formed by the rays through the ecliptic center C straight to Mars's position on the equant circle. That's all that line connects. So CF, CZ, CY. As such, this arc or interval carries no real meaning. It doesn't have an astronomical meaning. Yet, it provides Ptolemy with the means for computing the planet's eccentricity by comparing the apparent arcs and these arcs that I've now described. So these lines or these arcs function as a kind of scaffolding for his procedure. I think that's the metaphor I would use. And this is really the heart of Ptolemy's iterative procedure. If in the first iteration Ptolemy calculates Mars's eccentricity on the basis of the observed arcs and the arcs of uniform motion, it's the first line on the table, so now is when the table might become really useful. In the second iteration, the second line, Ptolemy matches the latter, so he's still looking at the same equant arcs, CF, ZH, but now he's matching them, or he's comparing them to these corrected arcs taken with respect to the excenter. So this is the fourth and the fifth column in the second row. He's calculating those corrected arcs, right? Those scaffolding that perform a kind of scaffolding by means of the difference arcs, KS, LT, MY. So this is how Ptolemy worked through the entire procedure, which gave us the 13-point-something value of eccentricity, once again finding a new value of Mars's eccentricity, although he omits the calculations themselves so as not to lengthen the procedure, he tells us. So chapter 7 of book 10 could be even longer. This new value for Mars's eccentricity results in a new position of the deferent center D, because it results in a new value for EC. That's the last column in the second row. Though he always places D halfway between C and E, but the new position of D in turn provides Ptolemy with new corrections for the ecliptic arcs, so with new values for the difference arcs, which are then used once again to find Mars's eccentricity and the apsidal line, then again bisect EC and do the same procedure again. So Ptolemy does go through this procedure 3 times in chapter 7. This is why it's so long. Now, when does Ptolemy stop the iteration process? How does Ptolemy know when to stop the iteration process? The short answer is Ptolemy's iteration process is carried until it reaches the point where there is simply nothing to iterate. More precisely, Ptolemy stops the iteration process once it no longer produces significant, noticeable corrections to those ambiguous scaffolding arcs taken with respect to the eccentric. This is when Ptolemy proceeds directly to testing the model against the original observations given at the beginning of the chapter. If Ptolemy's model is correct, then the ecliptic arc it yields will match his observations. And by plugging the arcs of Mars's uniform motion into the corrected model, whose double eccentricity equals 12, when the radius of the excenter is 60, Ptolemy indeed obtains the exactly same ecliptic intervals as he receives from the observations. And that's his desired proof that the model has the correct parameters. If in Ptolemy's treatment of the inferior planets, the size of the epicycle is what Ptolemy determines first, recall that Mercury and Venus make the epicycle visible. When it comes to Mars, determining the size of this epicycle is Ptolemy's very, very last step in the argument. And that's chapter 8 of book 10. To calculate the size of Mars's epicycle, Ptolemy looks at the observation of Mars made very shortly, just a few days, after one of the appositions employed in chapter 7. And these few days are sufficient to render the epicycle of Mars visible. So Mars no longer appears as if its motion on the epicycle did not exist after those few days. And at that point, determining the size of the epicycle presents no difficulty for Ptolemy. Mars's epicycle turns out to be the largest compared to the size of its eccentricity among the superior planets. So comparable to the epicycle of Venus. And I've already told you the ratio, it's 2 to 3, almost. This means that when the epicycle of Mars is at the perigee, and Mars is on the perigee of the epicycle, so at its closest point to us, the observers, Mars is about 5 times closer to the observer than it is at the apogee. That's how great the variation is. So just think of what the variation in size has to be, if that's the case. Okay, conclusion. So what I've tried to do in this lecture is to argue that it is in his encounter with Mars that Ptolemy develops the notion of the equant. So it's customary to say something, a few words about the title in the beginning of the lecture, but that's what I want to conclude with in this case. And I'm telling you this in the very conclusion of my lecture because it is something that I myself realized about my own title very late in the process. So it is only fairly recently, after I've already submitted the title for publicity purposes, that I realized that the very title of my lecture favors the conjecture or the position that I'm arguing for. So it's as if I've stacked the proverbial deck. Recall that in his investigation of Venus, Ptolemy first determines the deferent center, but then he doubles the eccentricity of the deferent, and that's his equant center. So that's book 10, chapter 3. When it comes to Mars, on the other hand, Ptolemy determines the equant center first, then he reduces the eccentricity of the equant by half. He bisects it as a step in the iteration process. That's how I've introduced that step. And that becomes his deferent center. So it is really only in the Mars chapter and the rest of the outer planets that Ptolemy bisects eccentricity. In the case of Venus, he does not bisect eccentricity, he doubles it. This wouldn't be an issue if Ptolemy stuck to the expression doubling the eccentricity in the Venus chapters and only employed the phrase the bisection of eccentricity in the Mars chapters and in the chapters devoted to the rest of the outer planets. But that's not the case. There are several moments, and I'm going to give you one. That's quote 15 on the handout, the final quote. Ptolemy employs the term bisection universally as a kind of a general descriptor of how single eccentricity becomes double. So that's the example, the quote 15 on the handout is from book 9, chapter 5. For all planets except Mercury. So notice that he is not restricting himself to the outer planets. He's talking of all the planets except for Mercury. That's because Mercury is just a very special case. It has its deferent sort of circle around the ecliptic. So the model is in some ways much more complicated. But for all planets except Mercury, Ptolemy claims here, the deferent center is the point bisecting the line joining the center of the eccentric, producing the anomaly to the center of the ecliptic. So it is as if it's not me, but Ptolemy himself who has stacked the proverbial deck. And the very expression, bisection of eccentricity, may be the most powerful argument for the Martian origins of the equant, insofar as this expression itself betrays the equant's Martian origins, possibly. Okay, that was the first conclusion. I have a second conclusion. It's short. So let me take a step back here. While I've tried to argue for a position with regard to the genesis of Ptolemy's equant, ultimately, to lay my cards on the table, any attempt to reverse engineer the Almagest will remain conjectural. Ptolemy has covered his trail all too well. So while it is useful and fruitful to ask about the background, conceptual or empirical, of the Almagest, I am not too committed to either the Martian origins hypothesis or the Venusian origins hypothesis. And I'm not saying this to sort of to not defend the position I've just argued for. In a question period, I'm happy to do it. This is just a kind of a... so I take a step back, but then I will return to where I was. So I'm not too committed to either hypotheses. I think ultimately we will just never know. It may be that the kind of thinking, right, that went into the Almagest, that goes into any project of this degree of complication, is itself too complicated to apply an order to. Be that as it may, and here's the real reason why I wanted to focus on Mars. Ptolemy's discussion of Mars provides what I would call a privileged workshop, or a privileged lab, maybe, for investigating how Ptolemy's mind works and how he develops his model, or at least it tells a likely story of how Ptolemy's mind works. This is so because in the Mars chapters, as luck has it, Ptolemy's order of exposition almost perfectly matches Ptolemy's conjectured order of discovery. In other words, the Mars chapter tells us a realistic story about the equant and its genesis, whereas the Venus chapter does not lend itself to such storytelling, or at least I haven't been able to read it that way. So the Mars chapter provides us with a fairly unique opportunity to glimpse Ptolemy's live practice of ancient astronomy. That's what I've tried to reconstruct in my lecture. And ultimately, this is what makes the Martian origins hypothesis more attractive for me than the rival Venusian origins hypothesis. Thanks.